This is, high performance computing. It's a very neat facility they have put here, and I have used it extensively for genome mapping and several other stuffs. So yes.
Thank you, Kasturi. My name is Ali Siavosh. So one of the sysadmins that works here. So you either if you have had an account here and have been using, possibly we have been in communication before. If not, and if you need it, the first thing is sending us an email on hpc_admins@nyumc.org. I'm going to talk about it later on. And then we will provide you with the account, and then all of the information that you're going to receive today would make a bit more sense and would be a bit more applicable. So we are going to talk about what high performance computing is. I learned that there are different levels of background here, so I'm going to try to make things as simple and build on it as much as possible. You are more than welcome to ask questions at any moment that you have it. It's fine. We rather first have the foundations solid, then we can build on it. High performance computing is a facility that provides you lots of resources, computation resources, for you to be able to perform any kind of calculation that needs large amount of RAM, large number of cores, processes, or a huge amount of storage, or a combination of all of them. Like any other computer, is practically when you log into the system, you don't see anything else more different, and not too different from a regular desktop or laptop that you are logging in. In the high performance computing, the way that you interact with the machine is through an interface. That interface resembles you the same facility or the same background or same facility is the best that you can expect from your machine. Like any other computer, when you are interacting with your computer and you're trying to do some calculation, you are interacting with operating system. With your software, you're running a software, and this software is actually communicating with the operating system, and operating system actually in a very low level communicates with CPU, RAM, and the I/O on the system. So practically, we are actually having the same thing over here. So you run a job, or you are doing a calculation. Your calculation would be in the form of an application. This application would run on operating system, and operating system would translate what your application wants from the CPU or RAM, and vice versa. The operating system that we are having here is a Linux operating system. In more precisely, it is a CentOS operating system, community enterprise operating system. We are on version 6.8 currently for our part of the computer, and for other parts which we recently updated it for some necessary packages. They are on 7.3, CentOS 7.3, which as a matter of fact is the newest version of CentOS. Linux operating system, as most of you have heard about it or have worked about it more often, has way more flexibility than a regular Windows or a Mac system. Over there you can change even the parameters of the very low level configuration files that you have, and you can make it to fit your needs to the best way. So this is something that most of the research environment are very big fond of it, and they use it, and this is the sole operating system in most of the research environments. In interaction with the cluster, just like in your desktop, you can use a GUI, a graphical user interface, which is more popular in a Windows machine, which is pretty much a point and click. But we strongly suggest that you use a command line interface. In a command line interface, you actually request what you want from the machine in the form of a command in a terminal. And the good thing about it is that it goes deep to give you any information about that process, and if it goes right or if it goes wrong. So command line interface would give you a good resource about your process and your command and what has happened, and also what you may need. And also it gives you way more option to play with compared to usual GUI interface that is very popular. So when you are logging into our machine, unless you are using particular applications, most of the applications are over there installed for using a command line interaction. By default, HPC or high performance computing is defined as an aggregation of computing power in a way that delivers much higher performance than what one could get out of a typical desktop computer or workstation. Roughly speaking, they say if you have about if you can put together 5 desktops to run a single task, you already started to getting into the border of the HPC or high performance computing. So the smallest cluster that usually people have, of course you can have a cluster only for one node, or you can have a cluster for more than like 2 or 3 servers together. But usually they say HPC starts about 5 times more power of a regular desktop. And it has become way more popular, and the results have been trusted fully that in most of the fields of science and technology, beside the experiment and theory, you rather to present your computational results to. And the computational result would be able to enlighten the future of what the project goes, because beside an experiment, particularly in experiment, you just can see what is happening. But for future, foreseeing what a simulation can go through, you just need a bit more details and a bit more understanding about the interaction in your system. So, a typical cluster or high-performance computing cluster is comprised of one head node and 1 or 2 head nodes and some other auxiliary nodes maybe, and then lots of compute nodes. The head node is the one that takes care of all the tasks in the cluster. And this is why we strongly recommend you that you don't do anything on head node. When you log into our machine, which is called Phoenix, where you land, you actually land on the head node. On the head node, the only things that we allow people to do is usually file transfer. If you need to move a file from somewhere to somewhere else, it's fine. But we do not like to see if a user is running a job or is doing some calculation on that, because it brings the whole system into a seize of power, and it can't really do the administrative jobs or tasks that it needs to do, and takes care of the well-being and operation of the rest of the cluster. So head node is what this is what head node is there for. Usually in our in other machines that we are actually going to purchase very soon, hopefully in next year, the first quarter of the next year, we are going to have a cluster which is larger and more component would be included in it. In those machines, we are going to have logging nodes. So we are not going to allow users to even land on the head node. They would land on the logging nodes, and when on the logging node, they can do most of their submission tasks and everything over there. Still, logging nodes are not there for computation. But the good thing is that if a user lands over there and they're like at any instance of time, actually on our Phoenix machine, there are about like 30 to 50 people on the machine actively working, roughly speaking. So if all of them want to do particular very demanding RAM demanding job, a login node will be able to handle it, but a head node, which is limited in amount of RAM and it needs some of the RAM for its own maintenance, won't be able to handle it properly. So when you land over here on the head node, you can ask the cluster to do something for you. We are going to talk about the details of what it, how it does it, but usually the tasks that you ask in the head node to do will be distributed to the compute nodes. So as a matter of fact, instead of like head node does it, it sends it to other nodes and say, okay, like you do this part or you do this section of the job, not even the whole thing. So that is all about the computation part of your job. But usually, as you know, you have lots of files with gigs and terabytes of data, gigabytes and terabytes of data, and those need to be processed in your calculations. Those files are stored in our storage system. We have one primary storage. This primary storage is very tightly integrated to the compute node. So each compute node has actually a dedicated network to it to talk with the storage. This network doesn't do anything else but communicating between all the compute nodes with all the storage nodes. So when you are, for instance, if you are running a job with like, you may say like 4 or 5 nodes involved in it, like if this is one node here, one node here, one node here, and one node here, and another node at the very bottom of the cluster, all these nodes would be able to go and talk to all of the storage nodes here. This is why the rate of the communication is very important for well-being of the job. Lots of jobs cannot wait for I/O to like pass through after some time. It actually after if it waits for some period of time, which is actually you can set it, but after that time it tells you like I don't get any response and the job dies. So this is why the network over here is very important. So this part, which is we call it primary storage, and currently it has about 1.2 petabyte of storage, which we are almost actually 85% full, is where your files land. When you log into the machine, you log in to somewhere which actually, if you look at the path, it is ifs home and your username, like in my case, SIAVOA01. This path actually exists here. Whatever comes after, like this is the ifs file system, whatever is on ifs is on a storage side. And the rest of the directory is actually where it's residing. So home directory is residing on ifs. Also data, which is another directory, is also residing on the storage. So all of the calculations that you do, either in your home directory or in your data directory, the process would be done here, but the data would be pulled away from, will be pulled out from storage, and finally at the end of the process of end of the calculation, it will be written back over there. This is why the interaction, as I said, the intercommunication is important. This is all about the primary storage. Primary storage is not only taking care of your calculations, but also it ingests data from different sequencers and other instruments. So as a matter of fact, when you get into the cluster, already most of the files that you need, if you're working with sequencers, is already there. We just need to provide you the access to the data, and this access would be after the owner of the data would allow you to do that. Most of the data that we have here are relatively sensitive, and it needs to be secured properly. So this is why accessing data over here, particularly in medical center and like some other industries, is very important. So the substantial amount of our time is taking care of the access of the data from one researcher to his or her postdoc or graduate student and vice versa. So that is what we provide. And the nice thing about the storage system that we have, which is called Isilon, and the other storage systems similarly do the same, you can fine grain the access. Like you can see, like one user would be able to read the data over here, but he won't be able to edit it. The other one can read and edit, but he cannot delete that file. The other user can read, cannot write, but can delete. So there's a different kind of combination that we can put together. Some users are only allowed to pass through some files. So when we are asking them, when they need access, they cannot access anything else but the final directory or final file that is here. They won't be able to see anything here. So they just need to pass through and get to their own data. If they want to land somewhere else here or here, they would get a permission denied error. Our primary storage is, of course, the one that's tightly integrated and all of the calculation is done on it. But our backup happens somewhere in Quincy, Washington. So every about 4 times a day, we mirror all the data that is here back to the Quincy, Washington. Just in case if the primary goes down for any reason, we would have a copy of all of the data and we can pull them back. So the largest amount of the researcher times that would be lost, theoretically, would be about like, you may say 6 hours, worst case 12 hours. Of course, pulling back the data is going to take some time, but from the time that the machine goes down, at most only 6 hours of the data may be lost.
How often did you have any chance to pull back the data? Or,
Usually, actually, very rarely, because we have another mechanism on our primary. On our primary, we take a picture of researchers' directories as well, upon their own request. Like they will say, I want the retention time of 3 weeks or 1 month. So every day, either once or twice or more often, we take a snapshot of that, and that snapshot actually stays here. If it happens that that snapshot goes away, still for about 1 month, that snapshot can be found here. So we can put it back, and only one time we needed to do it, and that was for another problem that we had, that we needed to take the data off of here back. Usually the line is not that fast, so if it goes like to the terabytes of data, then we are talking about days of data transfer that needs to be put back.
Does that happen often, that the primary could go down, or is it very rare?
Well, first of all, we knock the wood. It hasn't happened. Fortunately, so the system over here, as you see, primary has some nodes. It rarely happens that the whole system goes down. Usually, if it goes down, is either one of the nodes, or one of the disks, or one of the connections goes down. usually the way that they configure these clusters, they call it the high availability cluster. Means that for everything you have a spare, which is on the fail-safe mode. So it does not get activated unless it sees that the other one is dead. Then it actually switches every operation to the other spare part and it goes through. For instance, even for head node, we actually have a spare head node. If for any reason one of the, like the head node, that we call it active head node, dies, the passive head node always, like every 30 seconds, I think, or so, it sends a if you are alive signal. And if it does not receive it back, it takes over of all operations and disconnects all operations of the other machine. So that is, the same story in the different configuration here. Each of these nodes have two connections, as well as each of the nodes here have two connections. One of them is active, the other one is passive. There are other configurations also that they are both active, so that you can use both of them. So if one of them dies, you just see the lower performance on that connection, not necessarily switching between one to another. So this, as I said, it has never, I haven't seen it happening here in the time that I have been here. Of course, for according to the protocol, we need to have the backup in a geographically safe or distant from primary. This is why we put it on the on East Coast. So if I'm sorry, on the West Coast. So if on East Coast something happens, the other copy of the data, if in one of the coasts something happened, the other copy of the data is still available and can be retrieved.
So where is the virtual machine?
What's that?
Virtual machine, the HPC.
Virtual machine in HPC or generally speaking?
No, in HPC.
In HPC, when they are talking about, well, it really depends on which concept you are talking about. Or you are talking about the cloud?
No,
computing?
HPC VM0, where it is mounted? I mean,
HPC VM0 is actually nothing but a server here.
Oh, okay.
There is a server here. This server mounts, well, let me say it's here. There is a server here. This server mounts this guy and research Isilon, which is another cluster, both of them. So when you log into it, you can see both, supposedly. When the mounting process goes properly, you're supposed to be able to see both systems at the same time. This is why when you copy the data from your Isilon, from HPC Isilon to research or vice versa, this actually does not go through the whole, well, it goes through the network, but the process is like hard disk to hard disk. This would be treated like that, not necessarily being packed. So it is, this is why we call it VM0. We used to have VM5 VMs. They are decommissioned and recommissioned for other purposes. And VM0 is the only one that we actually keep for having a connection between these two. Reason being that these two are separated has been technical / security data. We are this cluster, this primary storage is actually fit or tuned for fast I/O. The one that's on the research Isilon, what they have is mainly a storage, so they don't need to react fast. They just need to have lots of huge amount of the disk space there, so people can put the data over there. So that's pretty much the story of what happens in how the interaction between different components are in our HPC facility. So a bit more details about the compute cluster, which we call it here Phoenix. Phoenix is 64 compute nodes, which they only have CPUs and about 256 RAM and 32 cores. 32 cores are actually hyper-threaded cores. They are actually 16 cores, but we turn on the hyper-thread so we can utilize as much as possible about those cores. We have a one, as people usually call it, one fat node, which has about 1 terabyte of RAM in it, and it has 64 cores. It's usually for processes that you need to keep a large amount of data in a fast access. Usually people use that particular one. Each of them have different queues. So if you want to use any of them, you need to log in or you need to request that node through the process of the submission script. We also have 5 GPU nodes. These 5 GPU nodes, they have 32 cores and 1 GPU card in them. That 1 GPU card is relatively old GPU card, and this is why we, one of the researchers actually purchased two new GPU node, but they have bought it for their own use. So they said for now we just want to be the sole user of that, but we are actually suggesting that if by any chance you are not using it, we can give you the highest priority of using that node, but if others want to use it and at the same time the node is not busy, that will be able to do that. They said, well, for now, because it's the beginning of the project, they rather to have it fully for themselves, but hopefully at some time we are going to have more GPU nodes available, and the request and need for GPU nodes are actually increasing substantially in the last couple of years, actually, I would say. Previously, only particular codes were able to actually utilize the GPU card. But now, there are more codes that they can do it, and of course, there are new applications which are GPU oriented. So we allow only those applications to be here. These are the nodes that I told you are equipped with the newest operating system. Because for those applications to run on it, they needed the newest operating system. So we converted them from the CentOS 6 to CentOS 7. And so they have a limited number of applications on it. Not all applications are on them. And if people want to, like, we recommend people to use these nodes only if they have GPU requested application to use it. Isilon storage, as you saw in the previous slide, there are 2 times 9 nodes, high availability storage nodes of total of 2.1 petabyte of data, which since it's mirrored, it is 1.1 in each of them, roughly speaking. The interconnect between the compute nodes and also storage and computation goes through 2 times 1 gigabyte. Remember, for the high availability, so all of these 2 byte means high availability. If one of them goes down, the other one takes over. So we have 1 gigabit per second, which is mainly used for management. Like if you log into a node and then if you log into the cluster and you want to go to one of the nodes, everybody will go through this one. But for data processing, we specified all of the nodes on 10 gigabit per second, which provides enough pipe or enough throughput for the data to be transferred between the nodes and from compute nodes to storage. Connection within the storage node. So remember I told you that all of those nodes are supposed to be able to talk with all of these nodes here. Reason being that all these nodes actually act as one entity. So these nodes need to talk with each other too. The talk between these nodes here are provided by InfiniBand, which is a faster protocol for communication. So that's why we are able to provide such a data ingestion, such a rate of the data ingestion for our storage cluster.
So what's the cost trade-off between GPU and any of the nodes? Like
cost rate?
Cost, yeah.
Well, each GPU card each GPU card is, depending on the model, is about $2,000 to $4,000. So one GPU node that we purchased and with 8 cards in it, like ended up about $25,000, $30,000. The regular compute node nowadays like goes down to something about $3,000 to $5,000, depending how much RAM you want on it. So mainly it is the card, and of course there are some components that comes with the card, like the V-Link, which provides the communication between cards. There are like 2 different types of it. They call it like a all-to-all or like a square. In all-to-all, all GPU cards have a direct connection to each other, so they can talk directly from one to another one. Each GPU card has about, the one that we have on the new machine has about 11 gig of RAM, local RAM on it. So as much as you can increase that one, or you can have a better communication between them, a synchronized or a concerted job on several GPU nodes would perform better and faster. This is how all of these components, as I told you, look like. In Carlstadt, New Jersey, we have our high-performance computing, Phoenix, and all the storage. What you see here is actually the storage part. Yeah, we recently actually added 2 more nodes. One of them is here, the other one is in the neighboring rack. And the computes are all in the other nodes, in other racks behind them. Each of these racks, I believe, not each of them, every other one, has a switch up there that provides the communication between the nodes from one to another. And this is a cable that you will be able to actually, if you want to directly talk to any of the nodes, you can directly talk to it, connect it and see what's going on. Because sometimes the node really goes down, and even the socket that is called IPMI can't talk to it. So you really need to just connect to it directly and see what is happening that causes problems. The storage is put in Quincy, Washington, and they are in only 1 rack of equipment over there, and it's mainly about like 3/4 full, and that's only the storage because we don't use compute over there. Recently, have been talks about moving everything to Quincy, Washington. I'm not the biggest fan of it, and of course there are some other parameters that gets into the decision, mainly because for some of the applications, users would really run into problem unless we make a very good high caliber data pipe between here and there. You won't be able to use that. So that project was kind of went down. So we saw that we have a cluster with God knows how many nodes on it, and you want to run your job. The job that you are running, if you want to utilize a cluster properly, you would use your code in a parallel environment. Your code needs to be written to be able to utilize a parallel environment. So the code that you are writing needs to have particular derivatives in it that would be able to tell the machine that I am using parallel processes, so provide them for me. There are several different types of them. What we have majorly in our machine and use it very often is OpenMPI. It's a open source message passing interface. MPI is coming from there. In a parallel environment, mainly what happens is that when you are asking your code, for instance, to calculate, well, I am by default a chemist, so in molecular dynamics, you have a system has like, you may say like 1 million atoms in it, and this 1 million atom is all distributed all over the place, and you want to calculate how the system is evolving by time under some shock or under some heat or whatnot. There are two ways to do it. One of them, in a parallel system, what it happens, it reads in the system, and with those derivatives that you have put in your machine, it says, okay, divide my system. If I ask for 10 or like for 12 nodes, it divides my system to the, okay, this one is 8, divide my system to 8 different sections. Each section would be assigned to one node, and the calculation would happen on that node. So all of the data from the head node or from the very major script would be distributed there. The result will be gathered, sorted, and will be put out as the final result. As far as I've seen, we actually encourage you guys to get more into the parallel programming if it's necessary for your job, because it gives you a way higher benefit. But there are some codes that do not run unless it's parallelized. And we use the OpenMPI to compile them, so all of those derivatives that you put in the code would be meaningful to the system, and they would do all of these division that they need to do for your file and process them chunk by chunk. So this is, roughly speaking, how your parallel system is going to work. But as you know, there are hundreds of users. To be more updated, about 850 users that we have right now on this machine. And about 50 of them actively, like almost every day that you go there, you see about 30 to 50 people logged in and they're working their job. So if all of them want to use these facilities, they need to have a system to receive their request and spawn them upon the availability of the sources and how and when they requested it. In our system, we have a queuing system that does the job, and it's called Open SunGrid Engine or Open Grid Engine, OGE. What it does, you actually make the request after running the job from it. It receives it and it puts it on a queue to see like what you are asking. For instance, you have asked for 20 cores and you have asked for like, I don't know, 10 gigabyte of RAM. It immediately looks to see if those cores are available for you or not. And another piece of information for you is like each node has about, each person has a quota of 400 cores and about 12 terabytes of RAM. In other words, you can request that much amount at any instance to run your job. In other words, it means that if you submit a job with like, I don't know, 5,000 SAP or children jobs, only 400 of them would run at once. Or 400 core would be dedicated to that job at once. So if you ask, for instance, if you in your submission script, you ask for 500, that would stay in the queue forever. It's not going to run. And then most of the time when a job is not running, it's because their resources that you have requested are not available. So this is very wise to practice to how much core and how much RAM you possibly would need for your job. Request that much, so if it is adequate enough, it would spawn to any of the nodes and starts running the job. So this is how the queuing system works. And at the very end, we have different kind of settings. On the queuing system, for instance, as one of the example, you may say, I want 20 cores, but I want all of those 20 cores to be on one node. Or you would say, I don't mind. I can actually have all of these 20 cores distributed wherever it wants. The second part is a bit more favorable for running the job, but it may run slower because all of those nodes need to communicate to each other. But in the first part, if you find a node that 20 cores are available on it, your job would run and would run fast. But the problem would be if such a node exists. Like most of the time, you may actually see that the cluster is quite busy, so not all jobs will be able to run with the requested resources.
Lee,
Yes.
Would it make sense for this map reduce framework implemented on these, or how does that fit in?
At this moment, we are not seeing that to be actually done. We are talking about like implementing.
Yeah, yes. I mean, is it possible, or does it make sense to do that?
Not with the current state that we have. As a matter of fact, I know that we have been thinking about putting together a storage that actually runs like that. Get the benefit of it, but not on our current system. So we are a little conservative about the system because the system needs to provide the resources to everybody, and so we try to make it as least specific as possible to particular projects. But that's something that we can actually. I know that the talk has been out there, and I think even there are a couple of the servers that they do in Excel. But I don't know how we can get it. But we like to see and of course, just like the GPU node, if the necessity goes and the demand goes as high as that we really need to do something about it, then we possibly will go for a separate system that will run Hadoop on and connect it to compute source. But so far, it hasn't been. Yes, so this is the story about the queuing system and how it works and how it reacts. As you could imagine, when you ask a queuing system to do some job, it specifies some of the resources for you and it keeps a record of what is available and what's not. So at any instance of time, there is a file that has all of the information of how many cores of which node is taken and which one is available and whatnot. Somebody remind me to talk about queue logging later, so I can actually connect what I said at the very beginning and the very end together. So how about we got all of the information about the configuration and the components of the HPC, but what happens as you are logging into a HPC system? As you log into a HPC system, first of all, we need to create an account for you. For instance, an account like that with your own Kerberos ID will be created for you, and you will be informed about this account that's created and it's available for you. You need to create some SSH key, which would be the security measure. Instead of password in some other system, you use the SSH key and the passphrase. So you will be able to log into your machine securely, and you will be sure 100% that your files and everything is safe and nobody else has access to it. So what happens when you log into the system? Let me see if I can actually this is what happens when you log into the system. You first face a message of the day announcement to you. You have logged into a compute cluster that's called Phoenix, and it has some components available to it, and if there is some important message, we're going to keep you informed about the machine and whatnot. It gives you also some information about the machine. It runs on CentOS 6, as I said. The cluster manager ID is number 2. This means that this is the second head node that you are logging into. And the cluster manager that's actually running the whole thing together is the version 7.3. Cluster manager is pretty much what keeps all of those components together. it is actually just like any other program. It's a program that takes care of the registration of the all nodes and compute nodes, and even if there are other nodes, specific nodes, it keeps the record of all of them, so you can add, remove, or convert one node to another one. So when you come here, as you see, you will see a prompt over here, demo at Phoenix 2. Demo is my, I logged in as demo, so I am the user. So when you log into a machine, as most of you possibly have known, maybe it's a repetitive thing for you, there will be some parameters assigned for you. These parameters, which I would show you in a very little manner, or very simple manner over here, are these parameters. These parameters are set at the very beginning by these defaults at the very beginning for you. So when you log into the machine, these parameters are there. Most of the time, when you try to run a job and you see that the job is not running, or there is some weird error, or it says like the component doesn't exist, this means that this variable is not set properly for you. This is why we come to the concept of modules. Every application that you need to use, well, 99.5% of the application that you guys need to use are put in a sort of environment which is called module. If you need to run a particular program which is called like SAM tools or web tools, the first thing that you need to do, you need to call the module and load it up. When you load the module, the additional parameters or some of these parameters would be converted to work with that program properly. So first, you need to know which program you're going to use, and secondly, we highly recommend you to use, to actually even be careful about the version, because some of them are version dependent to each other. If you call one of them without like saying which version, it would get actually the latest one or the one that we define as a default version. But as you see, with a comment called module avail, you can see what modules are available actually here for you. These are all programs that you can have access on this course. There are some of them actually that there are several different versions of them. This is why, for instance, for fast QC, you rather to choose which one do you want. If you don't choose it, uses the very last one. So there are like, I don't know how many of them, but most of them are actually repeated of different versions of it, because codes are evolving very fast in this environment, actually, compared to any other environment that I have been. It is like a database type thing. And some of them are even developed, not even, as we say in Farsi, it's not well cooked. So they just put something together and put it out, and then go and try to use it. Both users and sysadmins run into trouble when they are trying to compile it, to put it on the system, because parameters are not set properly, or it's not fitable to our system. As I said, our system is CentOS. CentOS is something which, for those you guys that know, is actually like a Red Hat-based system. We see more and more often that a code is developed on Ubuntu, and it uses all of the Ubuntu libraries, and it comes up and says, yeah, this is the code. They announce it outside that this is the code that we can use. And when you go and try to install it, you see, well, a lot of inconsistencies are in the code, because it's actually developed on different platform compared to what we have here. So these are the modules that I was telling you about. For instance, you even have like Python, which is compiled with two different compiler. So in spite of the fact that they are the same package, but they are compiled with different packages, so they can perform in different stages or in different cases differently, or faster or slower or whatnot. So what you do, you call one of these modules. As I said, when you call one of these modules, for instance, you say like Python 2.0 2.7, load Python 2.7 for me, it brings up and sets it does all of these things in your environment. So the environment that I showed you, all of those variables, these things are going to be either added to it or prepended to it. So those variables are going to be changed to something new. It really matters how we are adding it together. One of the researchers that we have here, he has his environment not properly set. He himself didn't properly set it, and now it's very difficult to figure out where the problem comes from. Why? Because we say, go and look the package over here, but he himself is loading something else, says go and look the package somewhere else. And depending which one is coming first and which one comes second, it may actually choose the wrong version, wrong dependencies, and a whole lot of errors may come up, which is sometimes even difficult to dig down what the problem is. So all of these things happen. So this is very important for you to have and load the module and prepare the environment properly for yourself to work there. In your environment, for some of the variables that is set, and it may be useful for you, there are something like home. If you echo $home, it will tell you where your home directory is located. You can do the same thing for users. So these are the variables that is set for you upon logging in. And these are the variables that will change. In this case, for instance, they are prepend. Means that this package would be having priorities to what anything else in your system that you call. So that's what happens in the environment. You're there, you have set your environment and you want to use. Lots of commands over there. You can actually find there are about 600 to 700, actually 600 to 850, depending on the version of Linux that you use. There are different commands over there available. There are some of them like ls that you can use, and you can list the content of your directory. A very good command that you would possibly need if you start using the cluster more often would be a man command. Man would be the manual. So if I type, for instance, over here, and ls, it tells me what options do I have to use. So I could say man, I could say ls-a. It tells me everything over there, even the hidden files. So these kind of things are some, this is the advantages between command line and GUI. Over here you have so many different options that you can apply to your commands, and you can get different output upon your need. It is way easier to manage and manipulate the data and your files when you're using a command line interface, of course. So you can, this is how you get yourself familiarized with the commands that you use very often. List, remove, copy, move, all of these things you can get one after another. If you are not familiar with Linux, we are actually having a wiki page that upon creating an account, we are going to send you that wiki page, and it has a good resources of not only how to use the cluster, also a couple of the resources that how to get yourself familiarized with Linux system. So you have files and directories. As I explained it for you, file structure on the cluster happens on ifs, or the storage part is where home and data and some other files are residing. but there is another file structure on the head node which doesn't have anything to do with the storage, of course, because it's used for its own use and its own functionality. It has its own file structure over there. But whatever is on ifs is the one that resides on the storage. Most of the time, when researchers are actually doing, as I said, you would never use this part. You're mainly using here from whatever happens from here down. And of course, in each home directory, one of you get one space. Upon creating an account for you, you will have 200 gigabytes of disk space available to you. And if this is not enough, you would contact us and we would increase it for you to your needs. And but for keeping things in order, we give the initial quota of 200 gig to each user.
If people aren't supposed to use the head node, like why do they have to act? Like why would they even be able to? Like there's no way that it could be.
Well, there are several ways to limit people. Well, okay, so this cluster was purchased such with head node and blah 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 blah, and adding another component to it is a little bit time consuming and needs manpower, which we always have been in season of manpower. This is why some of the emails that you send may take a bit longer to be responded. But you're right, like we shouldn't even allow users to ever land on head node.
Mm-hmm.
And this is why the
Is there
concept.
ever a reason why you would want to? Why someone would
To the head node, for a user, never. As a matter of fact, this very thing that I wrote here is very fact that I am recommending everybody to, after login, use Q login. Just issue Q login. When you issue Q login from the head node, you will be sent to another node. That node has everything that you may possibly need. If you want to copy the data, if you want to move data, if you want to even import data from outside, everything can be done. So head node would be actually let alone for doing whatever it needs to do, and you would have a Q login session on one of the compute nodes. You would do whatever you need to, and afterwards you log out, because the Q login is set over there for a short interactive job. If you have a job that's going to take more than a few hours, you are using another command which is qsat, and we're going to talk about it later. You're all encouraged to use one of the Linux-friendly editors, and there is a very big reason for that. One of the very naughty problems that we have is that a user finds a script somewhere, and this script does this and that, and they are working on a Windows desktop. They say, oh, wonderful, copy. They go and highlight everything here, and then they go here on Phoenix, and they say, okay, like VI something or nano something, open a file and paste everything here. You look at it, exactly the same. In your eyes, everything looks exactly the same. You save it and you start running the job. Here comes an error that even when I was seeing it first time, I had no idea what's starting off. Like it was saying that this command doesn't exist in queuing system. And you go there, first of all, you put the command outside of the script. qsat is outside of the script. But you say qsat this particular script, and it says this command does not even make sense. You go back and forth. What is it all about? Till someone tells you, or you realize that there are some hidden characters here. The hidden character would come exactly after some of the parameters that has been defined here. It comes here because you have cut it from the Windows, put it here, you don't see it. So if the Linux system is going to read it, and since it's coming from Windows, it doesn't understand the meaning, and it errors out something totally irrelevant. So this is why we recommend everybody to, first of all, increase your Linux experience and use editors which are put over there. In any research institute that you land, Linux would be the demanding and commanding operating system. You rather to familiarize yourself sooner rather than later.
Ali, one quick question.
Sure.
If it's recommended that it's better to queue login, why can't we directly redirect anybody who's logging into the master node to queue login, and after that, if they want to get back to master node, they can do it, right?
Yes. I don't really know why it hasn't been done before, particularly for the fact that some of the, I am really against installing some of the packages on the, because on head node you're actually running out of problem, and some little configurations are different. But let me see if I, there is, I can't think about any reason that why you don't redirect everybody directly over there. Like you need to put something in the config file that whoever logs in, who logs in them afterwards directly. One of the little problems that actually recently I realized, there are so many queue login sessions. Yes, queue login session, people forget to log out,
Right.
and if they forget to log out, even if they like, what do you say, like close their laptop or just, it stays there.
Right.
It stays there, and nobody knows, even the user doesn't remember that he has had or she has had a queue login session, and then a large amount of resources are still assigned to it, and this is why we are saying that after queue login you log out. So those resources will be released for the next user. We actually started, because we saw this problem so often, we started putting together a little script that after every 24 hours, we are going to kill any queue login session, that's all. Which, of course, we have had some complaint about it, because some people really need a very long queue login session, but at the same time, they need to be able to actually write it in a script and run it as a script. If they don't do it, there is
And Bash RC would, if you put a queue login on, at least when we start it, right? I think .bash RC would automatically queue login, right? We can put it.
.bash RC.
Or,
Well, I'm not sure if actually it would do it. I'm not sure. I haven't tried that. But you can like putting it in a C bash RC.
Yeah.
For everybody.
as soon as
will
the
log in it directly. Because even one of the, well, usually on the head node, so you directly go there, right? Wonderful. I'm going to put the queue login on everybody. So one of the nice things about this cluster is that you can submit a job from a compute node. Usually in other clusters, it's only head node that's allowed to submit a job. But for the necessity that has been running over here, and people needed to submit another job from a node, so all nodes are a queuing server as well, queuing client as well. So they actually can submit a job from one of the nodes to another node. And so this is another reason that I'm thinking that I can't really think about any particular reason not to do it. Let me discuss it in the team, and if this is the case, everybody will be logged in directly to one of the nodes. And I think that would be the best way to do it. So now you have your environment set, you know where you are, you know how much disk space you have, you know how much compute node, queuing system, cores, whatnot is available. Now we need to get to work. Those list of applications over there are the applications that usually people need here, and we put them there. they're mostly in the cluster. In couple of cases, we are having actually an interface for particular applications. So when you log in, you will not log into the head node. Actually, it's kind of recent changes, but I'm not sure how much of it will concern you. It would land you in that particular application only exists on something that we call it portal node. Portal node is one of the previous nodes that we had, and we kept it for the communication between the cluster and instruments. Like if you are running an instrument, one of the sequencers, like PacBio, recently actually, this was a story about it. In PacBio, you get all of the information, but you need to analyze it. Unfortunately, PacBio has an interface that only uses its own user and its own password, and it's a bit different than any other method that they have been using before. So we specified one particular node for this kind of interaction. So people actually log into that node, and they can run PacBio sequencer or any of those commands directly from there, and it will submit the job on either its own or send it out to compute nodes.
One question. So our PacBio tools have already installed?
It is the components are installed. There are some things that I know Mike has been in communication with Stuart and the PacBio team because there were some inconsistencies that we could not get together. But from software point of view, it is installed. I know that, and all of that story about that node was about PacBio. The latest advance of this can be actually asked from Mike. Mike was assigned this particular task. So, we learned about queuing system and everything, and now you want to run your job. How you run your job, you would tell your queuing system that I want to run this job. How you would do it, you actually run a script. In that script, you determine how detailed should I go to this. A little bit?
A little bit should be fine. I
Little
think,
bit. In this script, you say what parallel environment I want to use, how many nodes I want to use, how much RAM do I need. If my job runs longer than this time, kill it. If there is any change in my job, like if it starts, send me an email. If it ends, send me an email. If it dies, send me an email. All of these parameters, you can actually put it as different derivatives here. And at the very end, you say, okay, this is the command that I want to run. And then you say qsap. And most of the cases, you don't really even need to specify the queuing system unless you want to go to the GPU node. But we recommend to use -q all.q and then this script. The script, let's say submit dot bash or dot sh or whatnot. So queuing system is going to read in all of these parameters that we said and all of these commands, and then looks at the resources available and see all of these requirements can be satisfied in that particular node or in these particular nodes. Then it spawns the job, keeps a record of what nodes are actually in use, and do this kind of calculation and put all of the outputs. And after it is done, of course, if the user requires, send an email and also close everything and clean up. This is what in a very, 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 very simplistic nutshell queuing system does. There is a very good reason that we are telling you always to use qsub and qlogin, and we highly against anybody to SSH to any node. Reason being that when you SSH to any node and you want, for instance, do something which I haven't actually seen often, but it happens. If you SSH to a node, queuing system is not aware of what you are doing. So you SSH to a node and you start running a job over there. Queuing system still sees that node as an empty node. So someone comes and says, I want this to run this job, queue set this job for me. That job lands on this node, your job would die, that job would die, and it is not that clear to us unless we go and dig down to see what has happened at that moment in that node. This is why we recommend you to not SSH to node, and actually it is not even, it's allowed, but you shouldn't be doing it. Another point is the number of the cores or number of the jobs that you are requesting, it should accommodate with amount of the the job have as you are running it, it should accommodate with the number of the cores. For instance, there are some like a MATLAB job. A MATLAB job, I think, is one of those programs that it takes over any core that it sees on a machine. Unless you tell it that for each process, just take one core. So if you don't put that option over there, which is actually on our wiki, it lands on a node and it takes over all the cores. But from queuing system, it just has asked one core. And this actually happens a lot. There is a monitor on on the hallway that you can see the status of each node. Usually when this happens, the node goes red. Means that the number of the process requests for that node is way higher than what it's supposed to be based on the tree of the requests, as they call it. This means that one of these things has happened, and we need to go and dig down and tell the user that you haven't been using that particular option. Make sure that, for instance, if you are asking for 4 cores, make sure that your job is not spawning 16 of them at the middle of the Python script, because sometimes they do. They just like do it in like threaded system, and that 4 goes directly to 32 alt 7, and everything is submitted, or every resource is submitted without queuing system knowing about it. Yes?
In practice, how would you actually monitor that if you're to test run the scripts?
Monitor what?
Like how if it branches out into or expands into more than one.
When we see that this has happened, we log into the node and we check out what is going on, like how many branches are out there.
But how would like a user be able to tell, like, oh, I need to control for that expansion?
Well, that is something that actually should come out of the programming part. But this is one of the reasons that we actually recommend users to, if they are developing a code, first run a test run and see what is happening. How much RAM is requesting or taking. So all of these things with a short test, you can say if it is doing the job that it's doing. The problem comes that sometimes these requests are coming from 2 different nodes. Like people are actually piping things together. One of them is just asking for threaded. The other one at the very middle, nobody knows how it is running that particular process request. So like from 4 of them that you ask, each of them like says, as I said, as in the example, you will see. The best thing is monitoring it. You're running a job, you go to that particular, you submit it to a particular node, you can say that I want this job to run on a particular node. Go to that node and then do a QSAP. No, I'm sorry, do a top. If it is one process job, or do a PS3. If it is one process job, you see one line of what the parent is doing, what the child is doing, and how many is there. You go there and you see an R, like 4 R's coming, and each of them is actually getting to 8 more R processes. So it already, you see that it's already spawning more than what it's supposed to. So PS3, PS, top would all tell you what is actually in the top. You can specify like I want only the process and the child to be listed. So that is what I can think about if you get a chance. But usually, when that's as I said, that's the first thing that tips us about the fact that some programs are not behaving as they're supposed to. They are taking more, they are requesting more process requests than they're supposed to. Okay, you have started running your job, you have done Q sub or Q login to submit your job, and you started your job. If you immediately do a Q stat, which is status of the queuing for you, it will tell you which job is there and it gives you a record or a report about what you are having there. It usually are either in the state of R, which means running, or in the state of Q, means this is queued, or sometimes it's QE, means that it's queuing, but it's in a, Q wait, QEW, means that it is in an error state, but it's still waiting. Usually this happens when you ask a file which doesn't exist. Like you're requesting a file and you say the input file is somewhere. If it doesn't find either the input file or any other file which relates to the other one, you get to this guy and you see that there are some of them and it stays in the queue and they're not finding. This is very usual that happens. If you man queue stat, you see what you can actually, what kind of information you can get out of the queue stat. For instance, if you have a job running, queue stat -J and then the job ID tells you what is going on. Each time that you issue a queue sub, you get a report. There is a number, this job with this name, with this number is submitted to this node. That is job ID, the first number that you are getting. That job ID is where what you are using later on as the job is running to get information about it. QStat-J will tell you what actually has happened during submitting the job and what has been requested, and even if the job dies, QStat is not going to tell you anything because at that state you don't have that job running. There is another account and another command, Q account -J, same job ID. Same, this job ID number over here, it tells you a record about what happened and if the job completed properly or if it died. And usually there is some indication about what happened to cause the job to die. So this is the QStat. Something that's really very another source that gives you a lot of information about what has happened is the output file. In the output file, a lot of times that the job dies, there is an indication in the output file about what it has done. And there is some system message or something that tells you. This is why we always really like when you face a problem, the best thing for us is that you copy and paste the error that you are getting, including the command that you have issued. So we can actually reproduce the error and see where it is coming from, so we can dig it down properly. And also you have error files. So when you submit a job with QSub or QLogin, you have a, like if the name, if submit.bash, you get submit.bash.o and the job ID. Another file with E and job ID. In some other systems, you would have IO job ID and IE job ID too. These files are the output files and error files. If the problem comes from the code, that for instance you have defined two atoms that the atom doesn't exist, the error would go here to the output file. If the problem comes from the queuing system, for instance, it says like one of the processes that's supposed to run on that node unexpectedly died, the error would go here. So it's good to check out both of them and see what is in it. You will be able to debug your code way easier. For doing all of the, or most of the job that you need to do, you possibly at some point need to transfer data from your machine to the, from your client or your desktop to the cluster, or the other way around. All of the information about it is actually put in the cluster guide, but WinSCP, FileZilla, and scopy, if you're doing command line, would help you to transfer data from your client to the machine and vice versa. And of course, if you have any question, or you need an account, or you need more information about how much, what kind of resources you provide, or even the future of the HPC, you can ask us, and we'll provide you with as many information as possible. And I'll be more than happy to answer questions if you have. You know, they say that it's a very bad sign.
I mean, I'm simply amazed by how much you could pack this information in just 11 slides, you know.
Well, we actually do have several, some of them are for workshops that we have presented in stores.
Right.
Yeah, hand-on one, that is way more expensive. But since I don't know how much I should explain here, I kind of keep it as like notes for myself. But yeah, this I believe that you guys have the slide here, and so this link would give you lots of information about how to, what the cluster is and what is available over there to use, and if there is any extra. We face requests for installing softwares daily basis, few a day. So if there is particular software that you need to use, let us know, and we put it if it is HPC oriented. There are some of them are like a graphical one, and unless the code needs to be analyzed graphically, we don't see any reason for that. Like, we don't have web browser on computers because it does not make sense. Any resource that we are going to put there should be high performance computing oriented. There should be an element in it. So we'd be more than happy to install it over there for you, and more than happy to help you by any means if you have any question or need any help.
Thank you.
You're very welcome.